Hello, my name is Mikhail Zhizhin. I'm a mathematician, but for the last 10 years, I work in an applied field which is called remote sensing, specifically multispectral remote sensing of the nighttime surface of the Earth. It is like a scientific Buddhism. We turn our space-based telescope back from skies um, to our planet. And we see different pictures depending on the state of the Earth atmosphere and also state of the moon. Here at full moon, we see a lot of terrain, see land, ocean, quite a few city lights in the Persian Gulf. Then the moon is dimming. The terrain features tend to disappear and the lights get brighter. We see now cities, traffic on the highways, um, gas flares on the oil fields, and this type of no moon cloud-free data can be collected to make um, nighttime lights, maps of the nighttime lights of the Earth. This is an example of such stable map of a stable nighttime lights observed during the 2015. So it's an annual map where we take average brightness of lights not only on land but also at seas. And you can see the zoom insert in the corner our largest cities in Russia, Moscow and St. Petersburg. These maps of the annual and average brightness of the nighttime lights could be used as the basis to detect rapid changes in our noosphere. For example, 1st of November 2012, New York was hit by Hurricane Sandy, and most of the city has lost energy, and so the city lights were gone. It's possible to make a pseudo-color image where the unchanged lights are shown in yellow, the dimmed lights are in red, and green shows the clouds from the hurricane. This is 3 days after the disaster. Most of the power was restored, except some beaches in New Jersey. And then this is a full light, no change compared to the previous brightness. If we look on the downtown, um, uh, just with excuse that the resolution of the satellite is 1 kilometer per pixel, it's still possible to see that the Manhattan was still lit, but all the other downtown quarters were dimmed. Before this research, people were not interested in the lights in the ocean. It was thought that there is no lights. Here we have two adjacent orbits of the satellite overlaid on Google Earth with nighttime images of the Southeast Asia. Our bow detection algorithm can find on these dark orbits small insignificant spikes of light in the ocean. And these spikes are due to the fishing fleet, which uses lights bright lights on the boats to attract catch. On the photo, there are these light bulbs. It's usually 1 kilowatt bulb, and they are hanging in strings along the boat. So typical brightness of the fishing boat is comparable to the lights in downtown city. When we plot detections of all the boats in Southeast Asia, say for the year 2016, we can observe in the ocean very interesting patterns. We can see the routes of the boats. We can see the boundaries of the economic zones, and also we can see some strange regular patterns which are due to the self-organizing of the fisher. So they divide their zone of influence, like bees are building their hives, and we can see a regular concentration of the boat locations 1 mile apart, the most of the southern seas. The third family of algorithms deal with the multispectral infrared images taken at night. At daytime, infrared is mostly contaminated with the radiance from the reflected radiance from the sun. At night, we can clearly see in infrared, shortwave infrared, the gas flares. In midwave infrared, fires, steel mills, cement factories, volcanoes. This slide you can see detection and spectral unmixing of gas flare in Siberia. Using this method, we can estimate the temperature, energy, and as a result, the flared gas volume from this specific flare. When we count or sum up flared gas volume from all the flares within the country, we can estimate its footprint into the global climate change. Here we have histogram showing the most flaring countries in the world with division by year for the 10 years of continuous satellite monitoring. The country with the largest flared volume is Russia. Second and third place are taken by Iran and Iran. In the fourth place, there is the USA. If we just look for the number of the flares, the United States will be the dominant. They have twice as many flares compared to Russia, but they are smaller in size. We can report the observations in the media, and you can see the today result that the change in flare pattern in Mexico observed with our methods is taken seriously by the Mexican government, and the regulator probes the state Pemex oil company for the excessive flaring in the recent months. To sum up, you can see that this abstract mathematical algorithms applied to the very specific high volume of the almost empty nighttime images taken from satellites can help to monitor emergencies like power outages or explosions and fires. We can calculate independently and verify the state reports of the flared gas and company reports of flared gas volumes. We can track long-term trends in the economy, electrification, and ecology. We can correlate the energy of city lights with the population and poverty. And also we can monitor seas to see the illegal fishing and to fight the illegal fishing, to stop the overfishing, and just to see how the people live on land and sea.